Welcome back, dear viewers. Today, we're diving into the fascinating world of generative AI. You've probably heard about AI's ability to understand and process data, but what if I told you it can create, imagine, and inspire like never before? In this video, we'll journey through the realms of generative AI. So, fasten your seatbelts, because we're about to embark on an incredible journey into the world of AI creativity. But before we begin, if you're new here, don't forget to hit that subscribe button and ring the notification bell so you never miss out on the latest insights into the world of AI. Now, let's get started. What is generative AI? Generative AI refers to a subset of artificial intelligence, AI, that focuses on developing models and algorithms capable of generating new data that resembles human-created content, such as images, text, music, or even entire virtual worlds. These models aim to understand patterns and relationships within existing data and then use that knowledge to create novel, original content that is similar in style, structure, or context to what humans might produce. Significance of generative AI in the field of artificial intelligence. Creative content generation. Generative AI has significantly advanced the field of creative content generation. It can autonomously create art, music, literature, and other forms of content, opening new avenues for artistic expression and creativity. For example, AI-generated artworks have been sold at auctions, and AI-composed music is used in the entertainment industry. Problem solving and simulation. Generative models are used to simulate and solve complex problems. They are applied in scientific research, engineering, and other fields to generate simulations, prototypes, and models that can help researchers understand complex phenomena and optimize designs. Data augmentation. Generative AI is employed for data augmentation in machine learning. By generating additional synthetic data, models can be trained on larger and more diverse datasets, which often leads to improved performance and generalization in various tasks, including computer vision and natural language processing. Natural language processing. In natural language processing, NLP, generative models like transformers have revolutionized text generation, translation, and sentiment analysis. They can produce coherent and contextually relevant text, making chatbots and virtual assistants more conversational and useful. Image synthesis and enhancement. Generative models play a vital role in image synthesis, enhancement, and restoration. They can generate high-quality images, remove noise, and improve the resolution of low-quality images. Applications include medical image reconstruction and the creation of realistic computer-generated images, CGI, for movies and games. Types of generative models. Several types of generative models exist, each with its unique approach to generating data. They include variational autoencoders, VAEs. Variational autoencoders are probabilistic generative models that aim to learn a probabilistic mapping between the data space and a lower-dimensional latent space. They consist of an encoder network that maps data into the latent space and a decoder network that reconstructs data from the latent space. Variational autoencoders focus on learning the underlying probabilistic distribution of the data. Real-world applications. Image generation. Variational autoencoders are used to generate new images in artistic applications and data augmentation. Molecule generation. In drug discovery, variational autoencoders generate molecular structures for new drug candidates. Generative adversarial networks, GANs. Generative adversarial networks consist of two neural networks, a generator and a discriminator, that engage in a competitive game. The generator creates fake data to deceive the discriminator, while the discriminator learns to distinguish real data from fake data. Over time, this competition leads to the generator producing increasingly realistic data. Generative adversarial networks are known for their adversarial training approach and their ability to generate high-quality, realistic data. Real-world applications. Image generation. Generative adversarial networks can create photorealistic images, which are used in video game design, movie special effects, and art. Style transfer. They enable the transfer of artistic styles from one image to another, as seen in applications like Prisma. Face aging and de-aging. Generative adversarial networks can make faces appear older or younger, which has applications in entertainment and forensics. Autoencoders. Autoencoders aim to learn efficient representations of input data by encoding it into a lower dimensional latent space and then decoding it back into the original space. Applications. Data compression. Autoencoders can compress data, making it easier to store and transmit. Image denoising. Autoencoders remove noise from images in medical imaging. Anomaly detection. Autoencoders detect anomalies in data, such as fraud detection in financial transactions. Transformers. Transformers are neural network architectures that use self-attention mechanisms to process sequences of data. While they were originally designed for natural language processing, NLP, their versatility has led to adaptations for various generative tasks. Transformers are known for their attention mechanisms, which allow them to consider all elements of a sequence simultaneously. They excel in tasks involving sequential data, such as text and time series data. Real-world applications. Language translation. Transformer-based models, like the Transformer and BERT, bidirectional encoder representations from transformers, have transformed machine translation and language understanding. Text generation. Models like GPT, Generative Pre-trained Transformer, are used for text generation, chatbots, and content creation. Image synthesis. DALL-E, a variant of GPT, can generate images from textual descriptions, demonstrating the versatility of transformer models. Principles behind generative adversarial networks, GANs. GANs are generative models that consist of two neural networks, a generator and a discriminator. These networks are adversaries, hence the name, Generative Adversarial Network. Generator. The generator's role is to create fake data samples that resemble the real data it's trained on. It starts with random noise as input and processes it through a series of layers to generate data. The generator's objective is to produce data that is so realistic that it can't be distinguished from real data. Discriminator. The discriminator's role is to evaluate whether a given data sample is real, from the training dataset, or fake, generated by the generator. It receives both real and fake data as input and outputs a probability that the data is real. The discriminator's objective is to correctly distinguish between real and fake data. Training process. The training process of GANs involves a competitive game between the generator and the discriminator. Initialization. Initially, the generator generates random data, and the discriminator is trained on the real data. Adversarial training. The generator creates fake data samples and sends them to the discriminator. The discriminator evaluates these samples and provides feedback to the generator. If the discriminator correctly identifies a sample as fake, the generator adjusts its parameters to generate more convincing data. This adversarial loop continues until the generator produces data that is very close to real data. Convergence. Ideally, as the training progresses, the generator becomes skilled at producing data that is nearly indistinguishable from real data. At this point, the GAN is said to have converged. Transformative impact of transformers in natural language processing. Attention mechanism. Transformers employ the attention mechanism, allowing the model to focus on different parts of the input sequence when processing each token. This mechanism enables capturing long-range dependencies in language, making it more effective for understanding context. Parallelization. Unlike previous NLP models like recurrent neural networks, RNNs, transformers can parallelize computation across tokens, making them significantly faster to train and evaluate. Transfer learning. Transformers excel in transfer learning. Pre-trained models can be fine-tuned for specific NLP tasks, reducing the need for task-specific architectures and large amounts of labeled data. Scalability. Transformers can scale to handle sequences of varying lengths, making them adaptable to a wide range of NLP tasks. Capabilities of models like GPT-3. One of the most famous transformer-based models is GPT-3, Generative Pre-trained Transformer 3, developed by OpenAI. GPT-3 showcases remarkable capabilities. Text generation. GPT-3 can generate coherent and contextually relevant text, making it a powerful tool for content creation, automatic summarization, and text completion tasks. Translation. GPT-3 can perform high-quality language translation between multiple languages, enabling seamless communication across borders. Question answering. It can answer questions based on textual input, demonstrating the ability to comprehend and reason about the content. Text summarization. GPT-3 can summarize lengthy articles or documents, condensing the main ideas into concise summaries. Chatbots. GPT-3 powers chatbots that engage in natural and informative conversations with users, making them valuable for customer support and virtual assistants. Programming assistance. GPT-3 can generate code snippets based on natural language descriptions, aiding developers in coding tasks. Ethical considerations. Let's delve into the implications of generative AI and emphasize the importance of responsible AI use. 1. Deepfakes and disinformation. Deepfakes. Deepfakes are AI-generated content, often videos, that manipulate or superimpose one person's likeness onto another's, creating highly convincing fake videos. The ethical concerns related to deepfakes include misrepresentation. Deepfakes can deceive viewers into believing false events or statements, undermining trust in visual and audio media. Privacy violation. Using someone's likeness without consent for malicious purposes infringes upon their privacy. Potential for harm. Deepfakes can be used for harassment, defamation, or to create misleading political or social narratives. Disinformation. Generative AI can also be used to generate convincing fake text, contributing to the spread of disinformation. Ethical concerns include manipulation of public opinion. Disinformation can be used to manipulate public opinion, influence elections, and incite violence. Damage to reputations. False or defamatory information can damage reputations and livelihoods. Crisis mismanagement. Misleading information during crises, such as the COVID-19 pandemic, can hinder public health efforts. 2. Privacy concerns. Generative AI can inadvertently or intentionally violate privacy rights. Data privacy. The training of generative models often involves vast datasets, raising concerns about the privacy of individuals whose data may be included. Synthetic data. Generative models can produce synthetic data that closely resembles real data, potentially compromising individuals' privacy. Re-identification risks. Even anonymized data can be re-identified when combined with generative AI techniques, posing privacy risks. Surveillance and data mining. Generative AI can be used to enhance surveillance technologies, further eroding privacy. 3. The importance of responsible AI usage. To address these ethical concerns and privacy risks, it is crucial to prioritize responsible AI usage. Transparency. Developers should be transparent about the use of generative AI and disclose when AI-generated content is being employed. Consent. Obtaining consent when using someone's likeness or personal data in AI-generated content is essential to protect privacy and uphold ethical standards. Verification tools. Developing and using AI tools to detect deepfakes and disinformation can help combat their spread. Regulation. Governments and organizations should establish regulations and guidelines for the responsible use of generative AI, including data privacy and content generation. Ethical AI education. Promoting AI ethics education among developers, users, and the public can raise awareness of potential risks and responsible AI practices. Media literacy. Educating the public about recognizing and verifying potentially manipulated content is essential for countering disinformation. Transfer learning is a machine learning technique in which a model trained on one task or dataset is adapted or fine-tuned for a different but related task or dataset. In the context of generative AI, transfer learning has become a powerful approach for achieving excellent results even when there is limited data available. How transfer learning works in generative AI. Pre-trained model. Transfer learning typically begins with a pre-trained model that has been trained on a large, diverse dataset for a related task. In generative AI, this pre-trained model is often a language model like GPT-3 or a generative model like a pre-trained GAN. Task-specific data. For the new, target task or dataset, you have limited data. This data may be smaller in scale, domain-specific, or not enough to train a high-quality model from scratch. Fine-tuning. Instead of training a model from scratch on the limited data, you fine-tune the pre-trained model. Fine-tuning involves updating the model's weights using the target data while retaining the knowledge it gained during its initial training. Transfer of knowledge. The pre-trained model brings a wealth of knowledge about the structure and patterns in data from its initial training. Fine-tuning allows this knowledge to be transferred to the new task, helping the model quickly adapt and excel. Advantages of transfer learning in generative AI. Efficient use of data. Transfer learning maximizes the use of limited data. Instead of needing massive amounts of task-specific data, you can achieve competitive results with a smaller dataset. Faster training. Fine-tuning is faster than training from scratch because the model starts with a strong foundation. This saves computational resources and time. Improved performance. Transfer learning leverages the features and representations learned by the pre-trained model, resulting in improved performance on the target task. It can capture complex patterns even when data is sparse. Examples of successful transfer learning applications include language translation, audio and speech recognition, sentiment analysis, image classification, and many more. Generative AI in healthcare. Generative AI is making significant strides in transforming healthcare by revolutionizing various aspects of the industry. Here's how generative AI is driving innovation in healthcare. 1. Drug discovery. Generative AI is streamlining the drug discovery process, which traditionally has been time-consuming and expensive. Here's how it's contributing. Compound generation. Generative models can propose novel chemical compounds with desired properties, accelerating the drug discovery process. These models consider factors like bioavailability, toxicity, and efficacy, leading to the discovery of potential drug candidates. Target prediction. AI can predict potential drug targets by analyzing biological data and identifying proteins or genes associated with diseases. This helps researchers prioritize their efforts in finding effective treatments. Drug repurposing. AI can identify existing drugs with the potential to treat new diseases. By analyzing vast datasets, it discovers alternative uses for medications, reducing development costs and timelines. 2. Medical imaging. Generative AI is enhancing medical imaging techniques, aiding in faster and more accurate diagnoses and treatment plans. Image enhancement. AI-powered image processing can enhance the quality of medical images, making it easier for healthcare professionals to identify abnormalities or subtle details. Image segmentation. Generative models are used for precise image segmentation, which helps in isolating and analyzing specific regions of interest within images, such as tumors in radiology. Generative adversarial networks, GANs. GANs are applied to generate synthetic medical images. This is particularly useful when there's a shortage of labeled data, as GANs can create additional training data for AI models. 3. Data synthesis for research. Generative AI is instrumental in generating synthetic data for various research purposes, ensuring data privacy and availability. Privacy-preserving research. Synthetic data generated by AI can be used for research, when using real patient data is not feasible due to privacy concerns. This synthetic data maintains the statistical properties of real data while preserving privacy. Data augmentation. For machine learning research, generative models can augment datasets, making them more diverse and robust. This improves the performance of AI algorithms. Rare event simulation. Generative AI can simulate rare medical events or conditions that are difficult to encounter in real-world data. This aids in understanding and preparing for rare clinical scenarios. Generative AI has made incredible strides, but it's not without its challenges. Let's explore some of these challenges, shall we? First up, bias and fairness. Generative models can sometimes perpetuate biases present in their training data, leading to outputs that are unfair or discriminatory. Another concern is ethics. AI-generated content, like deepfakes, has raised ethical questions about misuse and misinformation. Evaluating generative AI is tricky. Creativity and quality can be subjective, making it challenging to develop robust evaluation metrics. Now, let's shift our focus to the future. Despite these challenges, generative AI is moving forward, driven by exciting research directions and emerging trends. First on the horizon is interdisciplinary collaboration. Researchers are working with domain experts and ethicists to ensure AI benefits society while mitigating risks. Explainability and interpretability are becoming increasingly important. Researchers are developing methods to make AI models more transparent and understandable. Sustainability is a key trend. Scientists are focusing on developing energy-efficient AI models to reduce the environmental impact of training. Customization and personalization are on the rise. AI systems are becoming better at creating content tailored to individual preferences. And, of course, ethics and governance are central. Robust ethical frameworks and governance mechanisms are being established to guide responsible AI development. In conclusion, generative AI is advancing rapidly, despite its challenges. As we navigate the waters of bias and ethical concerns, we're also charting new territories in explainability, sustainability, and customization. These emerging trends and research directions are shaping the future of AI, promising a more responsible and creative landscape. Generative AI is not just a tool. It's a muse, a collaborator, and a source of inspiration. It's showing us that creativity knows no bounds, and when we merge human imagination with AI ingenuity, magic happens. Remember, the future of AI is not just about algorithms. It's about what we create with them. So, what's next? That's for you to explore and for us to uncover together. Thank you for joining us on this journey. If you enjoyed this video and want to see more AI wonders, please give us a thumbs up, share your thoughts in the comments, and stay tuned for our next adventure into the world of AI. Until then, keep innovating, keep creating, and keep dreaming big.